Again, welcome to Mathematical Structure for Computer Science, CS 113, also known as Discrete Mathematics. In these lectures, we're going to study the concept of proofs or introduction to proofs. Our main objective, again, go through what is a mathematical proofs, also form of theorems, direct proofs, indirect proofs. Indirect proofs, we may go details when we start chapter 4. So it can be a proof for contrapositive and also proof by contradiction. So we start with the definition of a proof. So here we say a proof is a valid argument. Again, a proof is a valid argument that establishes the truth of a statement. So in mathematics or computer science, or even any other disciplines, informal proofs, which are generally shorter, are generally used. So informal proofs can have more than one rule of inference and are often used in a step. The steps can be skipped. Also, the rules of inference used are not explicitly stated. So it's more easier to understand and to explain to people. But at the same time also, it's very easier to introduce errors. Proofs are used in many practical applications, especially in computer science. So examples we have here including verification that computer programs are correct, establishing that operating systems are secured, enable programs to make inferences in artificial intelligence, also showing that system specifications are consistent. Again, these are some of the few practical applications that proofs are used in computer science field. So next we go to a theorem. A theorem is a statement that can be shown to be true using definitions, other theorems or axioms, such as statements which are given as true, and also the rule of inference. Mostly we can establish a theory based on the research that we did or experiment. So we may do an experiment, then whatever we discover from our experiment can be a theory of that very experiment. So a theory is a statement that can be shown that is true. So in this case, again, we prove the theorem. So we can use definition, other theorems, axioms, or rules of inference. Also, to helping a theorem, a lemma is a helping theorem or a result which is needed to prove a theorem. So again, a lemma is a helping theorem or a result which is needed to prove a theorem. Also, a corollary is a result which follows directly from the theorem. So it's less important theorems are sometimes called propositions. And also a conjunction is a statement that is being proposed to be true. Once a proof of conjunction is found, it becomes again a theorem. And it may turn out to be false. So forms of theorems. We say many theorems normally assert that a property holds for elements in a domain such as integers, the real numbers, or some of the discrete structures that we will study in this class. And often the universal quantifier needed for precise statement of a theory will be omitted by standard mathematical convention. So we have an example here. So we say that, okay, if x is greater than y, where x and y are positive real integer, then of course x squared should be greater than y squared also. But now, if they are not positive real numbers, let's say they are negative values, this rule will be false. So we say, okay, for all positive real numbers, s and y, if s is greater than y, then s squared is greater than y squared. And that's what it means. So this, again, a concept of a very basic mathematical theory. If we prove that if s is greater than y, then s squared should be always greater than y squared. Now, to prove a theorems, Many theorems may have a form like all x, p at s implied to q at x. Here we are saying that the p at x, if if p at s, then q at x for all x. So if s is integer values, then we can say from negative infinity to positive infinity. Now, to prove them, we show that where C is an arbitrary element of the domain. So here, to prove, we can say, okay, P at S should also be prior to Q at S, which means if P at S, then Q at S. Then here we are saying that if P at C, then Q at C. And here we're trying to prove. So we can show that C can be any value. Can be any. So here, by universal generalization, the truth of original formula follows. So again, we must prove something of the form P implies to Q. So we go to the P implies. So here we say if we know Q is true, then P implies to Q is true also. And we have this already in the truth table. The only time we can get false is when the Q is false, but P have to be false and true. If P is false and Q also is false, the outcome is still true. So that's why we say here, we know that Q is true always if we know P price to Q. So here we say, okay, if it is raining, then 1 equal to 1. By virtuous proof, if we know P is false, then P implies to Q is true as well. Now, if I am both rich and poor, then 2 plus 2 is equal to 5. So I cannot be rich and poor at the same time. And 2 plus 5 is not equal to 5, it's false. Here we see though, these examples sound again silly. Both trivial and virtuous proof are often used in mathematical induction. We may cover this mathematical induction concept in chapter 5 of the course textbook. So we can see a very nice example here. We're saying that, okay, previously we say P at S implies to Q at S, which means if P at S, then Q at S. Now, if that's the case, so if we have C as a value or anything, then we can also say that P at C should be implies to Q at C if X equal to C. So let's check this proof for an even and also odd integers. Now the definition tells us that an integer n is even if there exists an integer case such that n equal to 2k, and n is odd if there exists an integer k that n equal to 2k plus 1. So we know what is again. If n equal to 2k, there's integer k and n equal to, because here you can see that if you multiply any value, whether it's even number or odd number, by 2, automatically the value becomes an even number. 2 times 1 is 2. 2 times 2 is 2. That's both even number. 2 times 3, 3 is a odd number, but 2 times 3 makes it 6 even number. So that's our definition here. We can see our theorem for even numbers. Odd numbers, again, when we multiply 2 by any value, let's add 1 to it. So we change it to odd number. So now we say that, okay, we will need this basic fact about the integer in some of the examples proofs to follow. Again, we will learn more about this in chapter 4, especially when we talk about informal, like contrapositive, converse proofs. So proving conditional statement, we have P implies to Q, which is if P, then Q. Now for direct proof, we can assume that P is true. We assume that P is true. Use rules of inference, also axioms and logical equivalence to show that Q must always be true. So if P is true, Q must always be true. But sometimes if P is true and Q is false, the output will be false. So given a direct proof of theorem, if n is an odd integer, then n squared is odd. Example, 3 squared is 9, 9 squared is 81, 7 squared is 49, 5 squared is 25. So that's the rule we're trying to prove here. If n is a odd integer, then n squared is odd. Now let's see the solution. Assuming that n is odd, then n equal to 2k plus 1 for an integer k. Squaring both sides of the equation, we get n squared 2k plus 1. And 2k plus 1 all square will give us 4k squared plus 4k plus 1. Now, we can take the 2 out here, so we get 2k squared plus 2k plus 1. Now, if 2k squared plus 2k is r, then we can say we get 2r plus 1. Well, again, the r will be 2k squared plus 2k, an integer. Now, here we have proved that if n is an odd integer, then n squared is an odd integer also. So we can see the 2r plus 1. So proving conditional statement P implies to Q again. Here we have a definition. P implies to Q again means if P, then Q. Here we have a definition saying that the real number R is rational if there exist integers P and Q where Q not equal to 0, such that R equal to P divided by Q. If Q is not equal to 0, it's a real number and it's rational. Now, example here said we should prove that the sum of two rational numbers is also rational. So assume R and S are two rational numbers. Then there must be integer PQ and also TU such that R equal to P divided by Q, S equal to T divided by U, and U shouldn't be 0 and Q shouldn't be 0. Otherwise, R and S will be undefined. Now, when we had R plus S, we get PQ plus T over U. So here we have to find the LCM, which will be QU. Then QU times QU divided by P. So QU divided by Q and multiply by P. That will give me PU. Now QU divided by U, which is Q, and multiply by T. So that will give me QT. So here you can say, okay, our answer will be V over W only if W is PU plus, if V is PU plus QT and W is QU. And QU shouldn't be equal to 0. So here we can see that the sum is rational. And that's the definition also given to us. Now, proving conditional statement P implies to Q, another example here, we want to prove by contraposition. So here we are assuming that not Q, assume not Q and show not P is true always. So this is sometimes called indirect proof method. If we give a direct proof of not Q implies to not P, then we have a proof of P implies to Q. So we can prove that if n is an integer and 3n plus 2 is odd, then n is also odd. So the solution will be assuming n is even number. So n equal to 2k for some integer k. Thus we have 3n plus 2. We know this is 2n is 2k, so 3 times 2k plus 2, that gives us 6k plus 2. The common value of 6k plus 2 will be 2, so we get 3k plus 1, which is equal to 2j. So for j, we get 3k plus 1. The 2 will cancel each other, so j will give us 3k plus 1. Therefore, we say 3n plus 2 is even, since we have shown that not q implies to not p is p implies to q. Also, proving a conditional statement, prove by contradiction now. We say aka reduction and absurdum. To prove p, assuming not p, and derive contradictions such as p and not p, an indirect form of proof. Since we have shown that not p implies to f is true, it follows that contrapositive t implies to p also will hold true. So example here, we should prove that if you pick 22 days from the calendar, at least 4 must fall on the same day of the week. Now, assuming that no more than 3 of the 22 days fall on the same day of the week, because there are 7 days of the week, we could only have picked 21 days. This will contradict the assumption that we have picked 22 days. So again, proof by contradiction. We may cover that more in chapter 4. This is a preview of chapter 4. So use proof by contradiction to give a proof that square root of 2 is irrational. So suppose square root of 2 is rational, then there's this integers a and b with square root of 2 equal to a divided by b, where b again is not equal to 0. And a and b have no common factors. So here we get 2. Again, when we remove the square root, we get 2a squared over b squared, which is the same as writing 2b squared over a squared. Now, therefore, a squared must be even. If a squared is even and a must be even, an exercise, this is an exercise given to it. Since a is given, a equal to 2c for the sum integer c, that's 2b squared equal to 4c squared, which is the same as saying b squared equal to 2c squared. The 2 will go into the 4, and it will remain 2. Therefore, here we can say the b squared is always even because 2 times there. Again, then b must be even also. So if b squared is even, then b must even number. So, but 2 must divide both a and b. This will contradict our assumption that a and b have no common factors. And we have proved by contradiction that our initial assumption must be false. Therefore, square root of 2 is irrational. Next is proved by contradiction. So they say here we should prove that there is no largest prime number. Now, assuming that there is a largest prime number, call it P and lowercase n. Hence, we can list all the primes from 2, 3, all the way to Pn. None of the prime numbers on the list divide R. Therefore, by theorem in chapter 4, we can say either R is a prime or there is a smaller prime that divides R. This again will contradict the assumption that there is a largest prime. Next is the theorem that's a bi-conditional statement. A theorem that theorems that are bi-conditional statement. So bi-conditional statement, we say have a double arrow. If P, then Q. That's if else. By condition said if and only if P, then Q. which means only P will produce Q output. So here we say to prove a theorem that it's a bi-conditional statement, that is a statement of the form P implies to Q or Q implies to P, which is written here, P implies to Q or Q implies to P are both true. Now we should prove that the theorem, if n is an integer, then n is odd if and only if n squared is odd. Solution, we have already showed this in previous slide that both P implies to Q is the same as Q implies to P. So now let's see what is wrong with this. They say we should prove that 1 equal to 2. So the first step, I may have A equal to B. I square the A square, and I have A times B here. Now we want to combine A square minus B square equal to A times B minus B square. So we add minus B square to both sides. The fourth section, we get difference of 2 square. A square minus B square is the same as A plus B times A minus B. And here we can see that B is common, AB minus B square. So we take B out, we have A minus B. So we can see the A minus B on both sides will cancel each other. So left with A plus B equal to B, which is as writing that we get 2B equal to B and 2 equal to 1. So solution, step 5, A minus B is 0 by premise and division by 0 is undefined. So looking ahead, if we say if direct methods of proof do not work, then we may need a clever use of proof by contraposition or proof by contradiction. This is what we're going to cover in chapter 4. In the next session, we will use strategies that can be used when straightforward approaches do not work. So in chapter 5, we will see mathematical induction and related techniques. And also in chapter 6, we will see combinatory proofs. So proof is a very broad topic. It's a very broad topic. And as we see also, it's used in many computer science applications. So here we see later, we will see many other proof methods such as mathematical induction, which is a useful method for proving statements of the form or n and p at n, where the domain consists of all positive integers. Then we'll see structural induction, which can be used to prove such results about recursively defined set. We also have a Caton diagonalization, which is also used to prove results about the size of infinity set. Then combinatory proofs use counting argument. Again, we may cover this somewhere around chapter 6, 7, and also 5. So again, wish everybody the best and thank you for your time. In these lectures, again, we just went through the basic concept of proofs. And that's our topic, Introduction to Proofs. So we learn again what is a proof by definition, the application that they are used at, and some examples on proving some mathematical structures such as even number, odd number, or prove that x is greater than y. We should prove that x squared also is greater than y squared. Again, those are very basic concepts. So again, wish everybody the best. Thank you for your time.